Faraday's law of induction is awesome. I really like doing this. And the reason why I like doing this is because it helps me discuss, it helps me understand how electricity is made. So suppose we have a generator, a source of EMF, right? Do we understand what EMF is now? Electromotive force. For all general purposes, I can say that that's equivalent to V, but we know that it really isn't. It's only equivalent to V for ideal case scenarios. Okay, so what is the source of EMF? Some kind of generator. Now, how do we make a generator? A simplest generator is a wire moving in a magnetic field. Okay, suppose you have a area like that. What direction is this B field in? Into the paper, right? It's an X. Think of that as the back of your archery. Everybody did archery when you were in 7th grade, right? Or 6th grade or something, right? They all make you do that. Think of those arrows. What do the arrows have in front? A pointy tip? And what do the arrows have at the back? Feathers? Have you ever looked at the arrow from the back? They have crosses on them. That's how I think of magnetic field. Pointy end, if I see a dot, that means the field is coming towards me. When I see a cross, the field is going against me, like away from me. Make sense? So this field is going into the paper. Okay, now I said the simplest source of EMF is a wire moving in a magnetic field. Now, how do I know if I move a wire in this field? Let's say I have this wire and I move it in this field. How will I know that it's generating EMF? I have to make it into a circuit. And then I have to see if there is a voltage that develops across R, or if there's a current that starts to flow, right? That's the only way I'll know that this is working, correct? So that's what I have set up. Suppose this distance is H, and my field is contained in this area. And I'm moving my wire towards the right with a speed, say V. So for this case, may I write this E, my electromotive force, which is equivalent to potential difference, right? Because this is now going to be my source of the voltage or current. Will that be equal to F mag, oh no, not big F, little f. dl. Why F magnetic? If I move a charge through a magnetic field, what force does that charge experience? Q V cross B? Okay, so may I write this then as F magnetic divided by Q dot dl? Yes? May I replace F magnetic with QV cross B divided by Q dl. V cross B will give me a direction, right? V is that way, B is in to the paper. What direction will the current flow? Right? Clockwise? But may I write that as if I am moving with a constant velocity, can I take it out of integration? Is my B field constant? I can take that out of integration. What am I left with? And we find that the only value that makes any difference is the length. So E, in fact, can be written as VBH. Why do these segments not contribute? And why doesn't this segment contribute? Well, this segment cannot contribute because it's out of the magnetic field, right? So that takes care of that problem. What about the top and the bottom?
Because of the angle?
Yes, because of the angle. So we're only left with H. Okay, so E equals VBH. That is a very, very common thing that you will see all the time. Okay, now, do you remember when we were talking about magnetic fields? We said that magnetic fields don't do any work. But here I put it in, and it seems like magnetic field is doing work. Yeah? Q, V cross B. Look carefully. Who's doing the work?
The circuit.
Whoever is pulling the wire itself. Right? As soon as the wire stops being pulled or pushed, what will happen? It will stop. So it's the actual person who is pulling the wire that is actually providing the force. It's, again, magnetic field will do no work. Got it? It's the V that's doing the force. The fact that somebody is pulling it. As soon as that person stops pulling, E goes away. There's no current in the circuit. Okay, another thing that Griffiths does, and I want you guys to try it, is that he derives this pull force, and he derives the whole thing, and he says he develops the fact that that also comes out to be VBH by considering only the pull force, which is a really cool thing. I think I might have that somewhere, but I did those steps and they're a lot of fun. Where is it? Here. He talks about how the pull force is actually doing work, right? Because the fact that the pull force is responsible for doing the work is very important to understand, right? Magnetic forces do not do any work. This picture is very, very, very important. So I recommend for yourselves, please try to do this derivation. I think he doesn't do the derivation, but it's a lot of fun to actually just sit there and try to do it. Where is it? Where is it? Where is it? Actually, I'll show it to you. I don't think he does it, but can you guys see it? That's that picture. And then this is the derivation. So what I'll do is I will put this on, it's like a page long, but what I'll do is I'll scan it and put it with the lectures. So it might be useful for you guys to just try to walk through it. But I'll tell you the important part. So after the derivation here, okay, this is what I want you to realize. Number one, to calculate EMF, you must integrate around the loop at one instant of time. Whereas to calculate work done, you must follow the charge in its motion around the loop. Number two, always remember this. The pull force will not contribute to the EMF. Whereas magnetic force will not contribute to the work done. But together, the pull force and the magnetic force work together in order to make the whole thing go.